Okay, so off we go. Right, so last time we were talking about Green's theorem. Well, kind of. Last time we were laying groundwork for Green's theorem. We never got around to actually stating the theorem. We'll do that today. So let me just remind you, though, of some of the big ticket items that we talked about. First of all, we talked about reinterpreting this word boundary. Previously, boundary was just a curve, right? Boundary of a two-dimensional region is just a curve. It just sits there. Didn't have any sort of an orientation. Now it is oriented, right? So this is the important revision of the idea of boundary. Boundaries are now oriented. And in fact, they are specifically oriented according to this certain convention. Right here, we talked through those details last time. Ultimately, this convention about boundary orientations is kind of what makes the whole thing work. Okay, so there's that. Next, this idea of accumulation. Now, not a new idea. We talked about accumulations in various instances throughout this course. Specifically, anytime you do an integral, right? An integral is always capitalizing on the quantity in question having the accumulation feature. Because really, all an integral is just expressing the whole as the sum of the parts. Right? Chopping up into little pieces and then adding it up. So using the accumulation feature. So why do we have to make a big deal out of this? And that is because not everything has this feature. Right? You can't go around computing the whole as the sum of the parts if the whole isn't the sum of the parts. Right? It is very important that we don't over-assume such a feature. Next, we made this, I'm going to say, unexpected observation that boundary circulation actually has this feature. Boundary circulation is an accumulating quantity. Specifically, accumulates over areas. Namely, if you take an area, right, you look at its boundary circulation, then you chop that area up into pieces and look at the boundary circulations on the individual pieces. The whole is the sum of the parts. Doesn't seem like it ought to work. Seems like when you slice your original region into two separate pieces that you're adding boundary. And therefore adding boundary circulation. The thing is, the boundary circulation you're adding for the left is oriented that way. The boundary circulation you're adding for the right is oriented that way. Following the same convention on boundary orientations. And so, even though, I suppose in some sense we are adding some boundary, and we're adding in some sense two terms of boundary line integral, they cancel each other. And so, in terms of total boundary circulation, we're not adding anything at all. And so, accumulation. So, boundary circulation is something we can compute with an integral. Okay, now just a conceptual point. The big idea is, a lot of times we make the mistake of thinking of boundary circulation as something that happens on the boundary just because we compute it on the boundary, right? But very importantly, that's not really the way to think about it. Boundary circulation is something that we associate to a region, right? And this is an important point of view. After all, it is only because we start with a region that we even need to bother saying the word boundary, right? This two-dimensional region is something that when I take boundary and look at the circulation on that boundary, then I get the quantity in question. So even though we're going to be computing line integrals here, this is a quantity associated to the region itself. And therefore, it can be broken up according to little subregions. Therefore, boundary circulation has locations, even though it kind of doesn't feel that way. Don't fall for the red herring, right? Okay, and I think this is about where we ended last time. I'm pretty sure this is where we ended last time. So, okay. So, we have this new quantity, boundary circulation. It behaves like mass. It's an accumulating quantity. It behaves like mass in that it has location inside the interior. And if you think about it, That's all you really need to define a density, right? So in the same way that I can talk about, for a given area, right, I can talk about how much mass is in that area, and I can divide and talk about, therefore, mass per unit area. Specifically, this thing called mass density is the thing I multiplied times area to get mass, right? Well, let's do the same thing for circulation. We can talk about how much area there is in a given little region there. And I can talk about, well, how much boundary circulation do we have for that region? So boundary circulation, now again, I'm going to think of that as something that happens kind of in the interior. Don't fall for the red herring that it's computed on the boundary. Who cares? It's something that's really happening in the interior. And so likewise, I can talk about boundary circulation per unit area. Accumulating quantity per unit size, just like with mass. This is an accumulating quantity per unit size. In the same way that this is a density, we call this mass density because mass is the quantity. Likewise, we're going to call this circulation density because the accumulating quantity is circulation. Right, so totally analogous. Again, this is mass density. This is circulation density. And we do need to take a moment here to pause and just give ourselves a little time to choke down this seemingly pretty abstract idea here, right? Because it just doesn't feel like a stuff, right? Every density we've talked about in the past has been some sort of a physical stuff. This is not. This is an algebraic construction, right? But it behaves like stuff. So we're going to treat it like stuff. And in particular, as I just got through walking through, we have this related idea of density. Okay. All right. So with all of this noted, I do need to give you some notations before we move on to putting this all together. Let's see here. Let me get my, here we go. Okay, so that, boundary circulation per unit area. This is what we mean by circulation density. And here are various, here we go, notations and terminologies that we use to talk about it. So here's the formula. You want to compute this, take some little region, compute the circulation, boundary circulation going around the outside, compute the area, divide, take a limit as it gets smaller and smaller. You can do that calculation. It's in the book. It's not that bad. It's also, I think, just kind of, for our intuitive interests, I think not a critical calculation. Look at it if you're interested, but you don't really need to. But this is what the formula is going to end up being. This is how you compute circulation density. Rote and curl are some common notations for this. For reasons that will make more sense soon. These are common choices of words. And then let's see here. We also have Green's operator. I like to call this Green's operator because we're about to write down Green's theorem. And in fact, this operator will be the big operator, the thing that makes the theorem work for Green's theorem. So I think this terminology makes sense. And related to this terminology, I kind of like that notation, GRN, just a direct reference to, hey, this is Green's operator. Okay, and then the book likes this notation. I really don't care for this notation here. I'm going to put a frowny face on it. My problem here is you'll notice everything we've done here is in 2 dimensions. Right? We have 2-dimensional vector field, 2-dimensional regions in the 2-dimensional plane. This is intrinsically 2-dimensional discussion we're having, and yet they're talking here as if you can compute a cross product, this is a peculiarity of 3 dimensions. There is no 2-dimensional cross product. And K is the 3rd standard basis vector in 3 dimensions. Again, doesn't really make sense here. So I don't see how there's enough advantage to this notation to sort of offset the disadvantage of it not really making direct sense, right? So I'm anti that notation. Okay, but you'll see it here and there, including our textbook. Okay. And now we're ready. We have all the groundwork laid. We are ready to talk through Green's theorem. It's really just a matter of putting the pieces together. We've already established all the pieces. Step 1, we have this quantity called circulation that we've, before today anyway, before this section, before 6.2, we thought of this as being an expression, something that you compute. And now we're reconceiving this as a quantity, as a kind of a stuff. Right? So psychologically, that's kind of our first step, is to think of this as a stuff. Secondly, we know it's an accumulating quantity. Whole is the sum of the parts. And again, that's what this equation I have in green here, that's what that says. The whole is the sum of the parts, right? You just read it straight off the equation. Our little integral sort of shorthand for Riemann sums. And then lastly, we have this idea of a density, and that is that, keep in mind, if you have a certain amount of stuff that's contained in a certain amount of area, then the relationship is stuff per unit area, namely density, namely circulation density specifically in this case, and pick your favorite notation. I kind of like this one. I'm going to call it Green's operator. Okay. So notice all I did in this very last step, the orange step, if this will cooperate, is I have inserted Green's operator to represent our circulation density, namely that expression right there. Okay. So those are the big 3 steps as I see them. And we now have a big result, and I'll go ahead and highlight the result overall. If you want to compute a boundary circulation, so that's a vector line integral, and parameterize the curve, blah blah blah. If you need to compute a boundary circulation, what we see now is that instead you could get it by doing a double integral of Green's operator over the interior, namely over the 2-dimensional region whose boundary is your curve that you were interested in the first place. Okay. All right, so this is called Green's theorem. How we doing? Everybody all right? Okay. So let's see an example of this in action. Got to zoom back in. Okay, there we go. Okay, so we want to compute this vector line integral right there. Now, notice, you're going to find that this is often the case, by the way, in vector calculus problems. The following point. Questions will not announce themselves as being, this is where you're supposed to use whatever method. The question's just asking about a vector line integral. No comment as to what method you should use to compute it, right? So we're going to have to decide, or more generally, y'all are going to have to decide what method to use. We already know you can parameterize and plug and chug. That's a thing, right? That's from the last section. Let's talk momentarily about how undesirable that would be. Right now, it doesn't look so bad, but keep in mind that our curve is the unit circle. You're going to have to parameterize the unit circle. Not that we don't know how to do that. But when you parameterize the unit circle, x and y become cosine and sine, don't they? That means that when you actually do the pullback, this vector field, everywhere you see an x, you're going to have a cosine, or minus cosine, or something like that. Everywhere you see y, you're going to have a sine. And so some of these terms get a little weird. And so the integral that you would actually get if you were to parameterize and pull back, I'm a little scared. Does that make sense? Okay. So let's not do that. We have a brand new shiny theorem that we want to use that says, hey, if you want to compute a line integral, here's an alternative formula. We'd like to experiment with this if we can. However, there is a very important condition that we have to pay attention to. I like to make a big deal out of this because it's really, really important. It's also sort of understated in how it's written here. But notice, this does not tell you how to compute any old line integral you want. Green's theorem specifically only allows you to compute a line integral on a boundary, right? So this is a really big point. Boundary, right there. Right? Now again, subtle, right? But Green's theorem only tells you how to compute line integrals, vector line integrals on boundaries. Now, to the possible but that you might be thinking, oh, come on, that's some sort of mathematician formality. Who really cares? And how does this practically speaking affect the computation? Well, it does so in a very important way because only if you are actually talking about a boundary can you talk about what it is a boundary of. And this thing that it is a boundary of, that is the domain for the new integral. Right? So really importantly, I mean, even if you're not impressed with rigor and conditions and stuff like that, if your curve isn't a boundary, there is no domain over which to even talk about a double integral. There's no domain at all. If there were, then this curve would in fact be a boundary. So, really important condition. If you try to apply Green's theorem to a curve that is not a boundary, everything that follows is garbage nonsense. It has nothing to do with the question at hand. Does that make sense to everybody? So you can see how this is a dangerous landmine, right? You could totally step on it. Seems like a little subtlety in there, right? It's fine print almost. So please do be very, very careful about that. Now, with that in mind, let's go back to the example that we're looking at, and let's ask the critical question: is our curve a boundary? Now, again, very, very careful. Be super careful here. This curve, clockwise oriented unit circle. I'm not going to draw it all the way around because it's going to mess up my picture, but the unit circle here, oriented clockwise, is that a boundary? And tragically, no, it is not. Now, again, tempting to say it's a boundary because look, it goes all the way around and closes the little disc that you have right here. Isn't that what a boundary is? Not anymore. Remember, very importantly, the word boundary is a loaded word. Loaded term. Boundary means oriented, and specifically oriented according to our very strict condition, our very strict convention. And this is going the wrong way. So it's not a boundary. Everybody see that? Cannot apply Green's theorem here. Yet. So the clever move, right, is to make the realization that even though C is not a boundary, if I just orient the other way, right, remember we orient the other way by putting a little superscript there of a minus sign. Just orient the other way, you get this orange curve. The orange curve is a boundary, right? No problem. It's totally a boundary. It's a boundary of the disk exactly as it appears. And so this is the sort of little connect the dots that you have to make before you can actually invoke Green's theorem here. So step one is to realize that the curve oriented the opposite direction is what I need to rewrite this in terms of. Don't forget your minus sign when you switch your orientations. Then recognize that the curve going the opposite direction is a boundary. As we noted there, minus sign comes along for the ride. Of course, don't drop the minus. And once you have that it is a boundary, then yeah, sure, absolutely, no problem. Go ahead and rewrite with Green's theorem as a double integral. Yes?
You remember repeating why flipping the orientation made it a boundary? Like why was
Yeah, because the word boundary is this loaded term now, right? Boundary means not only is it the border between your set and not your set, right? But it also means that that corresponding curve is oriented according to the convention. And the original curve in blue here going the wrong way. But when I orient it the other way, this orange curve, this is following the convention. Namely, as I go along this orange curve, the set's on my left. And that's the rule. Is that cool? Yeah. Okay. All right. Now, we're not done. What we've done at this point is we've turned a question that I didn't know how to do into now another question that I'm not sure if I know how to do, right? So don't think of Green's theorem and the other related theorems that we're going to talk about in this next couple of chapters as being magic wands that just make answers pop out. That's not what they do. They have sort of a strategic similarity to substitutions. A substitution doesn't really evaluate integrals. A substitution turns one integral into a different integral. Maybe easier, maybe, not necessarily. Right, so that's what we've got here. We've turned a question that we didn't want to deal with into a different question, and now we have to decide, is that something that I want to deal with? Is that going to help me to get an answer to this question? Well, let's see by taking our vector field, F. Let's compute Green's operator. Now we have a formula for Green's operator right back here on the previous page. Whoa, here it is. Green's operator, aka circulation density, is this right here. It's the x partial of the second coordinate minus the y partial of the first coordinate. Right? Don't get distracted by the alphabet, the P and the Q of it all. That's not the point, right? It's the x partial of the second field coordinate minus the y partial of the first coordinate. And applying that to this question sure does work out nicely, right? And so this is why Green's theorem has helped us in this case. It's because it turned an integral that was looking pretty hard into another integral that I didn't really know what it was going to turn into, but it turned into an integral that's actually pretty easy. And then bam, answer. Everybody on board? Okay. Alrighty. Moving along. Another example. I've got a curve here made up of various line segments, like so. And I want to compute a certain vector line integral on that curve made up of 4 separate line segments. Now, again, you could brute force this, right? Because after all, this is just 4 line segments. Y'all know how to parameterize line segments. And you could take a deep breath and plow forward with that, right? The main downer being you would have to do 4 separate line integrals. And, you know, all else being equal, prefer not to do that. Okay, so what I'm going to do instead, I'm going to notice that my curve seems to kind of partition off a couple of regions there, and so I'm tempted, right, I have an eyebrow raised situation here. I kind of feel like maybe this is related to a boundary. Kind of looks like it's that purple curve is a boundary-ish. I know we had to be careful with orientations. So let's think that through. The way I'm going to do it is to break up this segment into 2 smaller segments. And then likewise, that segment, I'm going to break up into two smaller segments. So I'm going to view this not as a sum of 4 line segments, but now I'm going to view it as a sum of 6 line segments. And here's the good news. This part right here is straight up, no asterisk, a boundary. Orientations and all. So half of my problem, I could totally use Green's theorem details to follow. Is that cool? All right, so here's where it gets a little awkward, a little unfortunate. You look at the other half of the problem here, right? I've got these 3 line segments, and again, it's tempting to call this a boundary, but it's not, right? It's going the wrong way. It's going what you're going to want to call clockwise, right? So it's just not a bad. Doesn't follow the rules. But what that is just the exact opposite orientation of something that is a boundary. And if I look at just going the opposite way around, right? Look at these green arrows here. That is literally the boundary of D2, and what I have is just the opposite orientation of that boundary of D2. Is that good? And again, off we go. So we've related our curve to boundaries. Let's see here if I can denote so the curve being the sum of these two things, right? C is this plus that. Don't forget, opposite orientation gives you a minus sign on the calculation. Right? Now I have a couple of line integrals around boundaries. So to each one of these circulations, each one of these boundary circulations, I can just invoke Green's theorem. Right? Boundary circulation, double integral of Green's operator. Both sides. Don't forget your minus sign. Now we do have to compute Green's operator, but this works out actually really nicely. Green's operator is nothing to it. Let's see here. For this vector field, Green's operator is easily computed. It's just 9. Nice constant and everything. And so all together what I have is that I'm interested in let's see here, this integral of 9 computed over D1, so 9 times the area of D1, and then over on the other side here, let's see here, 9 times the area of D2. Casual glance at our picture, D1 and D2 have the same area. That difference is 0. Is that cool? Pretty happy? All right, so I didn't have to parameterize 4 separate things. Let me just make clever observations and invoke big theorems and avoid any real work. Okay. All right. Here's a kind of a corollary of Green's theorem. It's a very clever idea. Starting with Green's theorem again, here it is. All right, boundary circulation, double integral of Green's operator. Notice I'm applying Green's theorem to this specific, special vector field. 0, x is a special vector field. It's not uniquely special, but it is a special vector field. Why? What is it that's so special about 0, x? Well, I can compute Green's operator very easily, and the answer is 1. And it's really cool to have Green's operator be 1 because then this next integral is really easy to compute. It's just the area of the region enclosed, right? An integral of 1 over an area gives you that area. So what we have then is a vector line integral that computes the enclosed area. And that's a pretty neat trick. In some cases, that could be super duper handy. Now, before I take it to the next step, let me remind you of the coordinate line integral notation. Right? When you have a vector line integral, you can recall that the dx vector is dx comma dy. You could just punch up that dot product. And in this case, you end up with just x dy. So this is one of the rare circumstances where this coordinate notation is actually a little more compact, right? A little bit more streamlined than the vector notation. So in this case, I kind of dig it. Right? You don't have to; it doesn't matter, but it's kind of nice. Okay, second thing. If you're looking at a straight line segment, this is an independent little fact that we're going to discuss down here. If you're looking at a straight line segment, now again, reminder, y'all know how to parameterize line segments, right? This is a chapter 1 thing. Start here and there. It's going to be this vector plus t times the difference, right? So you can parameterize that, and if that straight line segment is the domain for integral x dy, then it turns out this is a really easy integral to compute. Now, there's some tedium in here. Not that bad. Easy to do. I encourage y'all to crank this out. On a line segment, this coordinate line integral will always give you the average value of x times the change in y. Real handy, real easy to remember. Okay. So now let's put these two pieces together, and what we have is actually a really convenient way to compute otherwise nasty areas. So here we go. Let's suppose I needed to compute the area enclosed inside of that blue curve. Right? How would you compute that area? And real quick, just for the sort of the nightmare of it all, let's entertain how we might do this the old-fashioned way. And you might be tempted, for example, to kind of break this down into several triangles. And what's that? 7 triangles. I can compute this total area as a sum of 7 triangle areas, and here's the problem. They're not right triangles. When the triangle's not a right triangle, it's a non-trivial trick to figure out how to compute its area. Right? Now, there's this thing called Heron's formula that will do it. But that involves knowing the side lengths, and of course all the side lengths are going to be square roots. So this is a nightmare of square roots. Best case. Right? So let's not do that. So here's where our corollary helps out massively. Let's see here. I'm going to argue first that, let's see here, this integral will compute my area. Then I'm going to argue second that the boundary is, well, it's just a sum of line segments. Right? There's 9 line segments here. The boundary is just the collection of all 9 of those line segments. And on each one of those line segments, I can compute the integral by just multiplying the average value of x times the change in y, tabulate, do the arithmetic, and answer pops out in your lap. So it's a really nice little streamlined method. Let me walk you through the first little bit of this. Let's see here. Looking at this first line segment right there. Right, looking at the very first line segment. Let's see, the average value of x. X begins at 1, x ends at 12, and that average is 6.5. Right, that's the average of the 2x coordinates. No big deal. Let's see, the change in y, delta y, well, y started at 1 and it went up to 6, and so delta y, let's see here, how to do it like that. Delta y is just 5. Easy arithmetic. I can multiply those and I get whatever that is, 65 halves. Now, that's for the first line segment. Now, you've got to repeat for all the other line segments. Yes, that is, It's going to take you a couple of minutes, right? It's not that bad, though. Notice no square roots, right? Really nice, no square roots. And no obscure references to obscure facts of geometry about, how to compute areas of non-right triangles or anything weird like that. So yeah, it works out really nicely. And in this case, the grand total area ends up being a nice, easy number. And it would have been prohibitively difficult to do this the other way. Everybody happy? Okay. All right. Okay. Turns out we can use Green's theorem to help us understand the idea of flux. We've talked about flux before. Flashback to chapter 3. Right? Big idea of flux was if you have a surface, right, with a flat piece of area, and if there is a fluid that's flowing through the surface, and if you know the velocity of the fluid, how would we compute the volume per unit time passing through the surface, right? So the flow rate. How do we compute flow rate from velocity? And the idea was this thing called flux. So this is kind of a two-dimensional version of the same thing. Here, instead of having a surface, I have a line segment in 2 dimensions. And imagine some sort of a 2-dimensional fluid flowing around. And if you know the velocity of that 2-dimensional fluid, you want to know how much area per unit time of fluid is passing through our curve. How would you compute that? And the answer turns out to be this right here. You're going to notice that looks a lot like the chapter 3 formula, the 3-dimensional flux. That's very, very similar looking expression. You'll notice that again, it makes reference to the unit normal vector here. That unit normal vector being the thing that you dot your vector field with. Morally, point being, I only care about the extent to which the fluid is flowing in the actual direction that's crossing the curve. I don't really care about the extent to which the fluid is flowing parallel. Parallel is not through. It's a nice little exercise. If you're in the market for an exercise, if you want to make sure that you understood that stuff back in chapter 3 about where we got the formula for flux. Take all the time you want, look back at that formula for 3-dimensional flux, and then adapt it to this 2-dimensional setting. It's a very, very highly analogous computation. You can almost kind of copy and then find and replace. It'll work through extremely analogously. Nice little practice problem. Okay, so that's for a straight line curve. Now here's a related idea. What if you want to talk about flux through a boundary curve? So in particular, you have some area, and then there is this curve here that is the boundary, cruises along like so. And you want to, I've zoomed in, of course, on just a piece of the boundary. It's actually going to go all the way around, something like that. If you want to know the total boundary flux being flow rate, quantity of fluid per unit time, outward across the boundary. This is another arbitrary convention, arbitrary but standard, and therefore not optional, right? So arbitrary but standard. How would you go about computing that on an entire boundary? So the very first thing I would do is I would come down here and say, well, look, the grand total, let me try to make some better color choices here, flux over the entire boundary. Well, I would focus on one little bit of boundary here at a time, and I would say, altogether, if I know how much flux there is through that piece, and then I add up on all of the pieces over the entire boundary, then that would give me the total flux. Right, whole sum of the parts. How are we going to compute the flux on that little piece? Well, we have a great little formula right here, right? For a nice little straight line segment that's flat, And constant vector field, no normal vector, boom, formula. Velocity dot normal vector times length. And that's all I do in this next step. That little piece of flux on that little piece of curve, velocity dot normal vector times length. This is a little piece of curve of length ds. And why don't we stop there? What's wrong with this as an answer overall? And well, the problem is that this answer is arguably kind of fine. There's really nothing wrong with this. It's just that I don't know how to compute these things, right? We don't have any prior experience with line integrals of a vector field dot normal vector. We've never seen that before. So this is a brand new kind of integral. We don't have any tools to deal with. All right, so here's how we're going to deal with that. We're going to come back up to here real quick. Reminder, we've got our vector field. We've got our unit normal vector. This is going to seem a little strange, but I'm going to take both of these and I'm going to rotate 90 degrees counterclockwise. Just bear with me for a moment. I'm going to rotate that 90 degrees counterclockwise, that 90 degrees counterclockwise. I appeal to your geometric intuition. If I have an outward normal and I rotate counterclockwise, I get, instead of a normal vector, I get a tangent vector. And furthermore, if I started with outward, not only will I get a unit tangent vector, I will get the correct unit tangent vector, because as I move in the direction of that vector, the region's on my left, as it's supposed to be. Right? So I get the correctly oriented unit tangent vector t. How do you rotate some arbitrary vector p comma q? Flashback to linear algebra. Remember, rotations are linear transformations. Linear transformations are matrices. Matrices are understood by their columns. Y'all have heard me say this a million times, right? Columns are the images of the standard basis vectors. So various little steps to be done there, but you can straight up write down a matrix that represents this rotation. And when you apply that matrix to p comma q, you'll get minus q comma p. Now, hopefully, possibly, y'all are all comfortable with all of that already. But if you're not, right, if you're not sure how to write down a matrix representing a rotation like this, come to my office hours. I'll be very happy to walk you through it. Right, this is something that we're going to be assuming that you're just good to go with. So come and discuss with me. Make sure you know how to do this. And again, the answer will be minus QP. Okay, so the punchline then is that I can rotate my normal vector to get a unit tangent vector, and I can rotate my F to get what I'm going to call F perp. And I claim that dot product and that dot product are the same. And this is just a matter of kind of thinking geometrically. I mean, after all, how do you compute a dot product? Various different options, but a dot product involves looking at the lengths and the angle between them. And when you rotate by 90 degrees, both by 90 degrees, it doesn't change the length. And it doesn't change the angle between them. Does that make sense to everybody? Okay. So this dot product's the same. Okay, who cares? What does this have to do with us? After all, we were down here. We were trying to compute this boundary flux. Well, check it out. I had F dot n, and now I'm just going to translate that to F perp dot t. And why does this help me? Well, this helps me because TDS is dx, and now we're back in business. Look at this. We've got our good old friend here. This is our regular old vector line integral, some vector field dot dx. We have tools for how to compute these kinds of vector line integrals. We know how to parameterize and pull back. We have Green's theorem. Right? We have options. So that's sort of the rest of this is just letting the cookie crumble. Here's Green's theorem. We have a boundary line integral computed as a double integral of Green's operator. Let's see here. How am I going to compute Green's operator? Okay, well now don't do this too quickly. A lot of people mistakenly here memorize Green's operator with letters of the alphabet, right? That's a mistake. It's not about the letters of the alphabet. It's about which coordinate are you taking partial with respect to which variable. And Green's operator is, let's see here, the x partial of the second coordinate. Now our second coordinate is P. Right? And then minus the y partial of the first coordinate. Our first coordinate here is minus q. Right? So again, don't do that too quickly. This is not going to be dq dx minus dp dy. Right? It's x partial of the second coordinate minus y partial of the first coordinate. After all, it's f perp that we're looking at, not f. Right? Is everybody happy with that? Right? Delicate little easy little landmine to step on. And now it's really all over but the shouting, and a couple of minus signs to cancel and rewrite. And check it out. Our new integrand is divergence. It's this thing that we saw back in chapter 3, oddly appearing unexpectedly for no apparent reason, so it seems. And there's our new theorem. So this is what we call, well, it goes by different names. I'm calling it here the two-dimensional divergence theorem. Some people call this the flux Green's theorem or the alternate Green's theorem, something like that. But we're going to, once we get into chapter 7, we're going to see what we're going to call the three-dimensional divergence theorem, and this is actually really, really similar to the three-dimensional divergence theorem. Okay. So let's crank one out. We seem to have a couple of minutes here. Suppose I want to compute the outward flux. Now, keep in mind this is through the unit circle, but we're going outward, and so this is, in fact, the boundary. So this is outward-oriented boundary flux. Right? We're given a vector field. We have our boundary curve. How are we going to compute that flux? Notice the scary first observation is that we don't know how to deal with that. Right? We did not previously have tools for computing in ds line integrals. So I mean, if you were gonna try to brute force this, you would have the nasty problem of trying to figure out how do I write down a formula for little n. Now it's not that it can't be done; you can totally do it. But kind of a pain. I don't want to have to think that through. The beautiful alternative then is just remember that we just got through developing a big theorem for computing outward-oriented boundary flux. Our new theorem says that outward-oriented boundary flux is a double integral of divergence. That's just copying straight from above. And now I'm just going to have to compute the, let's see here, the divergence of this vector field. Here's our vector field F, the divergence, easy calculation. Turns out to be -3, super easy integral. We're done. We walk away and declare victory. Everybody see how that goes? Nice little example. Is that okay? Looks like we are out of time. So we'll draw the line right there for today. See y'all later. Have a great weekend, and we'll pick up here on Monday. Don't forget about attendance if you came in after.